Alright, students, today we are going to discuss about the electrical properties of material. And first one is electrical conduction, which obviously Ohm's law comes into mind. And the Ohm's law is V is equal to IR. You can see the circuit area where I is the current ampere, V is the voltage in volts, and R is the resistance that is expressed in ohms, or this is the symbol of ohm of the conductor. Now resistivity rho is equal to RA by L, where A is the area and L is the length of the conductor. And electrical conductivity is 1 by rho, that is 1 by RA, and ohm meter minus 1, that is the unit of the electrical conduction. Now next in line is band theory. Now electrons occupy energy states in atomic orbitals. When several atoms are brought close to each other in a solid, these energy states split into a series of energy states or molecular orbitals. This is shown in figure that this is 2s orbital and another one is 2p orbital. The spacing between these states are so small that they overlap to form an energy band, that is interatomic spacing. Now same as band theory, the farthest the band from the nucleus is filled with valence electrons and is called the valence bond. The empty band is called the conduction band, and the energy of the highest field state is called the Fermi energy. There is certain energy gap called band gap between the valence and the conduction bands. Primarily 4 types of band structure exist in solids. You can see here the Fermi energy line. This is conduction band, this is valence band, this is again empty band and empty states, filled states, and you can see the overlap here. And this is the metallic portion of the total part, and this is the semiconductor where there is a clear gap between the valence bond and conduction bond, and to overcome this an energy is provided. And these are the insulator where valence bond and valence bond and conduction bond are far away, so the electrons don't jump, and that is why the insulation comes from here. The electrons can jump over each other very easily. Here we have to charge it by p type or n type, and here it cannot flow, almost cannot flow. So this is why the insulators are used when the electron flow is restricted or needed to be restricted. We are already talking about the band theory, and in metals the valence bond is either partially filled, that is for copper, or the valence and conduction bonds they overlap, that is in Mg or magnesium. Insulators and semiconductors have completely filled valence bond and energy conduction band. It is the magnitude of the band gap which separates the metals, semiconductors, and insulators in terms of their electrical conductivity. The band gap is relatively smaller in semiconductors, while it is very large in insulators. Let me show you the band gap once again. I have already told you that for insulators it is very large, and that is what was discussed below. The conduction mechanism: an electron has to be excited from from the field or the empty states above Fermi level, or for it become free and charge carrier. In metals, large number of free valence electrons are available and they can be easily excited to the empty states due to their band structure. On the other hand, large excitation energy is needed to excite the electrons in insulators and semiconductors due to the large band gap. The conduction in metals is shown as this one. And Fermi line, as I have already discussed, that is also shown here. Semiconductors like silicon and germanium have relatively narrow band gap, generally below 2 electron volt. Therefore, it is possible to excite electrons from valence to the conduction band. This is called the intrinsic semiconductors, as you have shown already. Every electron that is excited to the conduction band leaves behind a hole in the valence band. An electron can move in to a hole under an electrical potential, and thus holes are also charge carriers. You can see the whole mechanism here. That is, electrons and holes are both charge carriers here under a electrical potential. Electrical conductivity of a conductor primarily depends on two parameters: charge carrier concentration N and carrier mobility mu. The conductivity sigma is also written here. The inductive semiconductors are two types of charge carriers, namely electrons and holes, as I have discussed already in the previous diagram, that this is the hole which is also a charge carrier, and electrons are also charge carriers. Since each electron is excited, so this is the formula of this is the formula which is already denoted here. That is extrinsic semiconductor. The conductivity is enhanced by adding impurity atoms. That is called dopant in intrinsic semiconductor. All semiconductors for practical purposes are extrinsic. A higher valence dopant, that is P or in Si, creates an extra electron, while lower valence dopant like B creates a hole, that is p-type, as shown in the atomic bonding model below. Just look at the atomic bonding models. That is p here. Here p is a dopant which is creating free electrons, and here B is another dopant which is creating another type of holes, that is p-type holes. So that is n-type model and that is p-type model. Please look into the pictures very carefully. Just look at the picture very carefully. You can see the p-type atoms and the n-type atoms. The p-types, here boron is a dopant which is injected, and the holes are created. Holes are also electron carriers, and this is n-type, where electron subsidy is created. And okay, moving on. The band theory model of n-type and p-type extrinsic semiconductors are shown below. In n-type, for each impurity atom, one energy state, that is known as donor state, is introduced in the band gap just below the conduction band. In p-type, each impurity atom, one energy state known as the acceptor state, is introduced in the band gap just above the valence band. You can see the pictures here. The donor state for the n-type ones and the acceptor state in the p-type ones. This is conduction band again, and this is valence band, and this is the band gap between those two. So those are extrinsic semiconductors, and The extrinsic conductivity, the large number of electrons can be excited from a donor state by thermal energy in n-type intrinsic semiconductor. Hence, number of electrons in conduction band is far greater than the number of holes in the valence band. That is, n is greater than p. And in p-type conductors, the formula is written below. On the other hand, number of holes is much greater than the electrons. P is greater than n due to presence of the acceptor states. So go through the picture again. This is the donor state, and this is the n-type, and this is acceptor state. This is p-type. Here holes are created, and here excess electrons are created. So this is a graph stating the effect of temperature. The increasing temperature causes greater electron scattering due to an increased thermal vibration of atoms, and hence resistivity, that is rho, reciprocal of conductivity of metal, increases. Conductivity and decreases linearly with temperature. You can show the graph here also. This is the rho, that is resistivity, and this is temperature. The graphs are almost linear, you can see. The resistivity of metals depend on two other factors, namely impurity level and plastic deformation, as these generate the scattering centers for the electrons. Increase in impurity level results in more scattering centers and decreases conductivity. Similarly, plastic deformation introduces more dislocation, which will act as scattering centers and increase the resistivity. The formula is written here. This is the effect of temperature for intrinsic semiconductor. In intrinsic semiconductor, the carrier concentration increases with temperature as more and more electrons are excited due to the thermal energy. You can see the curves of germanium and silicon. With the variation of temperature, the carrier concentrations are increasing, and somehow within a part it is saturating as well. Here it is the effect of temperature for extrinsic semiconductors. The temperature dependence of extrinsic semiconductor, on the other hand, is totally different. For example, an n-type conductor exhibits three regions in the temperature versus the carrier concentration curve. This is the carrier concentration curve, as you can see. It is extrinsic semiconductor. So let me close the video for now, because we have enough material to be provided in the later half, and please study at home, and if you have any questions you can raise. I have also an online class in coming days, so we can discuss it with in that class later on. Thank you, and study well and stay safe. Thank you, everyone.